Okay. So as I told you that this session and the next session we will continue with a new chapter, and then I will give you more time to practice, and then we will have the exam. So the next chapter is called Primitive Functions and Simple Integrals. Today we want to talk about primitive functions. The first part, I think for the beginning at least, it might be good that we just consider this lesson as a mathematical curiosity. And then later when we start talking about integrals, we will understand why talking about this mathematical curiosity under the title of primitive functions becomes relevant from practical point of view. So today's lesson, if I want to summarize it, in the previous chapters I gave you a function and then you differentiate it and then you find a function. Now primitive function is the reverse order. So the derivative is given, you're supposed to find the primitive function, the original function. Yes. So why this becomes important in this lesson, and probably a few more lessons will not be clear. We just consider it as a mathematical curiosity, just like a game. And then we start talking about something very important that's called integrals. Again, it becomes not very clear why primitive functions are so important for the notion of integrals. It was Newton and Leibniz who discovered the relation between primitive functions and the integrals. Okay, so that, I mean, for the time being, don't try to look for some kind of motivation rather than just a mathematical curiosity, yes, like a game. So I give you a function, you differentiate, you get a new function. Now assume that the new function is given to you and you want to go back and find the original function. So that is the game today. So I need some terminologies and I want to define them. First, what do we mean by a primitive function? So let me start with the definition of this concept. A function and this is a standard notation. A function we denote it by capital F. A function capital F is said to be a primitive function of the function little f if the derivative of the capital one becomes the little one. Very, very simple idea. So example, functions capital F, let me put in 1 here, f of x equals to x squared and f2 of x, say x squared plus 1, are both primitive functions of the function little f of x equals to 2x. Since, why this is true? Very simple. You differentiate the capital F1, it becomes 2x, which is this function. or you differentiate capital F sub 2, and then again it becomes 2x. So the derivative of f1 and f2 are both equal to 2x. So according to the definition, capital F1 and capital F2 are both primitive functions for this function. Since you should write like this, f1 prime of x equals to f2 prime of x is equal to 2x, and it is equal to f of x. Yeah, is that understandable? So it means that if I give you a function and I ask you to investigate if this given function is a primitive function for another function, the task is simple. It's just nothing except differentiation, yes? So for example, if I give you g of x equals to x to the power of 3, is g of x a primitive function for this function? You would say no, because if I differentiate this function, the answer becomes 3x squared, and 3x squared is not equal to this one. So you say that f1 and f2 are primitive functions for f, but g of x is not a primitive function for f. Yes? So it's very simple, the idea. But the point is this. The point is that we are supposed to we want to find a systematic way to be able to find primitive functions. This is different from this problem. In this problem, I have given you the functions, and I am asking you to show that they are the right ones. Yes? That is easy. You just differentiate and see that this is equal to this one. So if I give you the primitive functions and I ask you to investigate, it is nothing except just differentiation again. Yes? But the point is that can we do some kind of systematic way to find this? The answer partially is yes and partially no, because there are many functions we cannot find primitive functions for them. If I give you any function in principle, you can differentiate it. But if I give you a function, it is not always possible to go back and find the primitive function for that function. Not among the functions that you know and they are famous. You can artifact some functions whose derivatives are those functions, but they are not among the functions that we know, okay? So, one thing that is clear, if I ask you for this example, can you give me another candidate for a primitive function? I don't think it is hard. So can you tell me what another function whose derivative is little f, yes?
X squared plus 2.
Plus 2. And this, so you see that this number that I add is not relevant. So in principle, if you want to write all of them, so you would say that f of x equals to x squared plus any constant that I like will actually be a primitive function for this function, yes? Because if I differentiate it, this important part will play the role, it becomes 2x, and this part becomes just 0. So it doesn't matter, these are just two examples of primitive functions for this function. But I can write f of x equals to x squared plus c. So I hope that you agree that all these package, every function in this package, for any choice of c that you like, is a primitive function for that function. But this is not trivial. Are they the only ones? So might be, I don't know, might be some genius person come in and find a very complicated function and its derivative becomes equal to 2x. At this moment, you might not be able to imagine that, but who knows? Might be, I don't know, we have a very complicated function, and when we start differentiation, a lot of cancellation happens, and those cancellation happens after that, this only survives. Okay? So that is a concern. That's something that you have to be concerned about. Are these the only functions with that property? Or might be someone can come up with another function, maybe complicated, but it's still its derivative becomes 2x. Unfortunately, mathematicians will be able to answer this. You will study probably university. The answer is no. So you don't need to be worried. these are the only functions whose derivative is equal to 2x. So if I give you this primitive, this is a primitive function for 2 f of x equals to 2x, that is not hard. That is at the level of high school. You just differentiate it and it becomes 2x. But if I tell you, are you sure that these are the only possible answers, the only possible primitive functions for 2x? The answer is yes, but not trivial. The reason that I say yes, because I have seen the proof, I have studied them, I know that this is true. But at this level, I want you to understand this is not trivial. Because as I told you, might be someone can artifact a very complicated function so that when you start differentiation, there are many terms involved there, they cancel each other, and so miraculously this happens, that the derivative is actually 2x. But the good point is that no, at least you can add to your information, your knowledge. It is not possible. Every other function whose derivative is equal to 2x is among these functions. Okay? Okay. But if you see, we have to start some kind of a little bit of guesswork. Do you remember before that, I gave you this table, and when we start completing it, so do you remember I gave you the function, I gave you its derivative here. For example, if I give you a constant c, its derivative is what? C times x. Oh, sorry. The derivative is 0. If I give you x to power a, its derivative is a x to power a minus 1. Then we continue this list. We also learned about the derivative of exponential functions. And then we learned that c goes down and the function repeats itself. Yes, and then we also learned what happens if I have a to power cx. C goes down, the function repeats itself, but you have to multiply it by an extra ln of a. Yes? So these are the functions that we studied when we want to differentiate. The whole process in this lesson is to reverse the table. Yes? So what I'm telling you, if I give you this function and I ask you, can you tell me a function whose derivative is 0? Of course you have it here. It becomes c. If I give you this function and I ask you, can you tell me a function whose derivative is this? Then the function is here. Yes? Yeah. So this is very simple. But the way that we want to do it, we want to change this a little bit. So instead of having this table, I want to ask this question, and I want to complete it as far as we can today, yes? I put a little function f here, and it's capital F here. So that is the primitive function for f. Okay? And now, on the left-hand side, I write a constant. A simple function, the simplest possible function. Then I ask you, if you don't mind, let me change the constant to k here. And there is a reason for that. So let me just call k. K is a constant. Okay, so can you tell me a function whose derivative is k? So if you don't mind, can you give me a function whose derivative is 1? Can you give me a function whose derivative is 2? What is that function? Yes?
So the first one, x.
The second one?
2x.
2x. If I ask you, give me a function whose derivative is 3, the answer becomes 3x. So if I ask you, give me a function whose derivative is k, kx. But if I ask you, give me all possible functions whose derivative is k,
kx plus c.
Yeah, then you need a constant c at the end. Yes? So this is why usually you see this in the integral table. So in the formula sheet, you will have 2 tables. Don't mix them up. One table is for differentiation. One table is for primitive functions. Yes? So if I ask you, did I do something very strange? No, I just guessed. I guessed a function whose derivative is this, and that remark I mentioned here guarantees that I don't need to look for somewhere else. These are the only ones. Okay? And I want to do some kind of guesswork a little bit more, and then hopefully at some point we will be able to find primitive functions or more complicated functions that we cannot usually do based on just guesswork. Okay? For example, let us just, before going back here, let me increase the level. So after constant functions, again, I want to have the simplest possible functions. Do you remember the logic behind that table? We started categorizing the possible functions because calculating the derivative all the time from the limit was hard. So we categorized the functions, and then we learned how to deal with each one of those individual functions. The same logic is actually more or less ruling here. So the next function that might be is complicated than just a constant function is just the function x. Yes? So if I ask you, can you give me a function? If I ask you the derivative of x, the answer is 1. But now I'm not asking you the derivative of x. I'm asking you, give me a function whose derivative becomes x. Yes? So what is your guess? You need to do some guesswork. And of course, after you guess, you can prove it by differentiating. So what's that function whose derivative is x? Yes?
X to the power of 2.
X to the power of 2 is a good candidate, but that's not true. Why? Because if you say x to the power of 2,
Then it's
Half
if
of
I,
x to the power
exactly.
of 2.
If I differentiate it, it becomes 2x. And then I do not see this 2 here.
Yeah.
So I have to compensate for this extra 2 that I don't need. And that comes from the fact that I put 1 over 2 there. If I already start with 1 over 2, then what will happen? Then this becomes 1 over 2, and then the derivative of this becomes 2x, but this 2 that is coming down is cancelled by this 1/2 that I anticipated it and put it here,
Yes.
and I will get x. Yes? That's easy. So we were able to find. So if I give you f of x equals to that, then what is capital F? Capital F is 1/2 x squared, but that is not the only one. If you want to write all of them, you have to write plus c. Okay, let us just expand this a little bit more. If I ask you to give me a function whose derivative is x squared, give me a function so that after being differentiated, the answer becomes x squared. The candidates are clear, yes? They should be some third power of x, yes? So, but the third power of x just like this doesn't work. Because if I differentiate it, it becomes what? 3x squared, but there is no 3 here, so I have to anticipate to put something there to cancel that one. Yes,
1/3.
1/3. So what you say is 1/3. You put it here, and I think now you can guess what happens if I have something like that. Yes.
Yes.
So what do you think would be a primitive function for this?
the integral would be 1 over a x to the power of a.
No. Now be careful. You see, when I started with 2.
A plus
The
1.
powers
A plus
are
1.
1 more, yes?
A
So this
plus
becomes
1.
1 over a plus 1,
Yeah.
x a plus 1. Yes? So that is what we want to put the second row. X to power a. So be careful. This is differentiation, but now this is the new lesson. So this becomes 1 over a plus 1, x to power a plus 1. But then you have a constant c at the end. Okay, so there are some articles that I wanted to make sure. So sometimes the book asks you about all primitive functions. Sometimes they ask about a primitive function, and sometimes they ask about the primitive function. So I want you to differentiate between these. If they ask about all primitive functions, they are asking you to put that c there, yes? If they ask find all primitive functions, you have to put this c there at the end, showing that c can be any number that it likes, but you have to write it. If they ask find a primitive function, then it means that they are asking for one of them only. You can choose whatever you like for c, but what is the best choice? 0. Yes. In that case, you really ignore C. Not ignoring it, you are choosing it to be 0 because you are asking about 1 and only 1. And about the there, you have to wait for the next lesson. Okay? So here, all primitive functions, they mean that you have to put C there. A primitive function, you don't need to put C. It means that you are choosing C to be 0. But for the primitive function, we have to wait a little bit. And of course, there is some exception for this formula. Do you see that exception? There is one exception for this formula, that this formula breaks down. It doesn't work. Yes?
What if A is -1?
Exactly. And then you have to wait until math 4. Yes? So what happens if A is -1? Of course, clearly I will have problems here because the denominator vanishes. But then that becomes what?
Not just -1, also a fraction.
No, it works. For fractions it works. Because this formula works even if A is fraction.
Really, if A in that one is a fraction, like 1 over
Yes.
1 over A, isn't that
the
-1?
exact, yes. So how did you calculate the derivative of a square root of x? Square root of x is x to the power of 1/2, yes? So this formula is valid for all a's, not just natural numbers. But the proof for fractions are hard and above the lesson. This is why we didn't do the proof, but we actually said that, okay, this will be true. But in this case, a can be any number, but except -1. So that's extremely important to put it here, that a is not equal to -1. You might ask, what happens if a is -1? If a is -1, I will have 1 over x. So my question is that, what is the function whose derivative is 1 over x? And surprisingly, you will see next year that this is natural logarithm of x. It's ln of x. So the derivative of ln of x turns out to be 1 over x. So it's completely different. Yes?
But a can be any other number,
Any other?
even negative numbers.
Yes, yes. The fractions, the square roots, and everything, except -1. For the case -1, this turns out to be 1 over x. And then if I ask you, can you guess a function whose derivative is 1 over x? You know the function, but you don't know why it works. The function is ln of x. The derivative of ln of x turns out to be 1 over x. Okay, so, but I think it is better to stop here, don't go further, because we can solve a diversity of problems even just using this simple formula. And you see that so far I just did some guesswork. And of course, after guessing, I can prove it. How can I prove that this is true? There is one way. If you want to show a function is a primitive function for another function, there's one way to do that. Differentiate that function to see if it works or not. Yes, let us do that. Let me differentiate this function. 1 over a plus 1, x to the power of a plus 1 plus c. Let me differentiate it. Okay, the derivative of the sum of two functions is the derivative of the first one plus the derivative of the second one. But that is a multiplicative constant, so I just write 1 plus a, and I differentiate this part. How should I differentiate this part? A plus 1 goes down. X to the power of a plus 1, 1 unit less. And then the derivative of constant is 0. But then you see that this a plus 1 and this a plus 1 are cancelled. A plus 1 minus 1 is just a. So this becomes x to power. So you see, I differentiate this function and I got this. So this means that this function is a primitive function, a primitive function for x to the power of it. Okay, but essentially we didn't do, we just guessed this formula is correct and then we proved our guess. Yes? But let me just try to solve some problems using this. Before that, I don't know, for some reason they don't even mention this, but it's not trivial. And they haven't used a symbol for that. I just want to follow your book. So in Swedish system, they don't use this sign for the integral. They only use this sign when they want to put numbers there. And they call this integral. But in higher texts, this is called definite integral. Without numbers is called an indefinite integral. An indefinite integral is more or less nothing except primitive functions, yes? So let us just stick to the notion in the book, and then I have to invent some notation for myself. So let me write PRN to denote primitive, okay? So this is not trivial, but you have to know. If I have a function, and then I multiply it by a constant c, and then I want to find a primitive function for the whole package, I don't need to bother about this constant. I just concentrate on finding the primitive function for f and then multiply it by a constant. Exactly like derivatives. Yes? So do you remember the one similar to this formula was this. Cf prime was Cf prime. Yes? If I want to take the derivative of a function which is multiplied by a constant, I just put the constant there and multiply it by the derivative of my function. The same thing happens if I want to find a primitive function for a number multiplied by a function. I just concentrate on finding the primitive function of the function, whatever this function is, I just multiply it by c. And the same thing is true if I have two functions added and I want to find the primitive function for the sum of two functions. So do you remember what was the formula for the derivative? It works there as well. So this becomes f prime plus g prime. Analogous to this is this one. It becomes primitive function of f plus the primitive function of g. By the way, this result follows exactly from this result. It's not something strange. And then, of course, if I have f minus g prime, this becomes f prime minus g prime. The same is true here. Primitive function of the difference of two functions is the primitive function of the first one minus the primitive function of the second.
Baba, I've never seen the word PRM.
No, this is my invention.
You just invented it.
Yeah,
Very
this-
nice.
We are not allowed to use that sign, so I just wrote this. Okay, so here I just want you to know that these are true. I don't know why they don't even mention it. It is not trivial that if you want to calculate the primitive function of the sum of two functions, you can act individually. Let me just write, even though I write it, but my experience shows that you don't care usually. You are not allowed to write primitive function of the first one multiplied by the primitive function of the second one. Write it once and cross it over for all, yes? And the primitive function of f over g is not equal to the primitive function of f divided by primitive function of g. That's not true. But fortunately, these three are true. Okay, now I think everything is ready, and then we actually try only today. I don't want to go that much, but I want you to give you examples of this formula. Okay, and then you see that even though we started from guesswork, but it turns out that we can really do much better. I can give you functions and I can ask you, can you guess? Probably you would say no, but if we calculate, we can calculate. And that is the power, yes? So this means it is, even though we started with just guessing something, but at the end, we are more powerful than just guessing, yes? Okay, so this is an example which is important for the exam, yes? Example. I will stick to this all so that you get used to. For the time being, let me just use all, yes? So determine all primitive functions of the following functions. Of each function. Okay, so let us start with very simple one. So I give you f of x equals to 5x to the power of 3. You are supposed to find all primitive functions for this function. So you know, you have this rule, and you have that formula on top here. Yes? So if I want to find all primitive functions for this, what I'm supposed to do, I write capital F, denoting the primitive function. That's the standard way of writing. 5 is a constant, so I don't care about 5, but I care about a primitive function for this. This is where either you have it in your memory or you refer to the table, but be careful you are not referring to the wrong table. They are very similar. So here is the table here, x to power a, the primitive function becomes here, and then 3 here is playing the role of that a. So if you want, you can just write all the details. It becomes 1 over 3 plus 1, x to the power of 3 plus 1, and then because I have emphasized on all, you have to respect and put c at the end. And then you simplify, of course. So this becomes what? So 5 times 4, it becomes 5 quarters, and then x to the 4th, and then you have a constant. So this is also easy. I think it was also easy to guess here. It was not hard, but let us see that. So if someone asks you what you have done, you would say that I found all functions whose derivative is this function. Yes? There are no other functions like that. So let us increase the level a little bit. So number 2, if I give you this function, 2x to the power of 5 plus 3x to the power of 2 minus x plus 2. We want to find a function, all functions whose derivative is equal to this function. So these are E-level questions, they are not hard. But you see that all these rules I need, because I have a multiplicative constant everywhere. I have what? I have the sum of functions, I have the difference of functions, so I have to use all these rules. On top of that, I should be able to use the first 2 rows here. Yes, you will see why. So what should I write? If I want to write all the details, I would write f, capital F is equal to 2 is a constant, I don't care. But x to power 5 becomes 1 over 5 plus 1, x to the power of 5 plus 1. Then I have a 3 here, multiplied by 1 over 2 plus 1, x to the power of 2 plus 1. Minus, the power is 1, so this becomes 1 over 1 plus 1, x to the power of 1 plus 1. And plus, so these 3, I use the second row, but the last one is the first row, because the last one is the constant number, yes? And it is k times x plus c. So what is k? K is 2 in this case, so the answer becomes 2x. And then
Plus
you
c.
put a constant c at the end.
Yes.
Wait, I have a question.
Yes?
Don't you put the C after each of the...
No, that is a good question. In principle, you should put different c's for each case. But you can say that, okay, all those constants with different names, I can absorb them and call the final a constant c. But that's a good question. So, here, what you do, you can simplify a little bit.
You get 1/3,
So this becomes 1/3, x to the power of 6,
then 1
and then this becomes just 1, just x to the power of 3,
and a half.
minus a half, x to the power of 2, plus 2x, plus c. So that is all primitive functions of that function. It means that I was able to find all possible functions whose derivative becomes this function. But still, I think still you could guess. This was not a hard word to guess in this case. But it becomes harder. For example, if I go to this, let me just write this one, a simple one. Number 3. F of x equals to square root of x. It's not that easy now to guess. If I ask you, give me a function whose derivative turns out to be square root of x. It's not hard to guess, but harder than the previous one. So, and then you will see that we can start using our systematic approach to answer this question. How can we do that? We cannot immediately start this process, because this function is not in my table, yes? Let me bring this a little bit more. Okay, because this function is not directly in my table. I have only two formulas in my table. One for a constant, one for some power of x. Yes? So this motivates me to change the form of this function first. So what I do, what I write in blue is part of the solution. Yes? First, I do not start with capital F. I just change the form it looks by writing it as 1 x to the power of 1/2. Yes? And then you immediately see that I have this formula in my table, but 1/2 is playing the role of that a. So now if you want, you can start the process of the primitive function. A in this problem is 1/2. According to that formula, you write 1 divided by 1/2 plus 1, and then you write x to the power of 1/2 plus 1 plus a constant. Yes? Okay, and then you have to simplify. 1/2 plus 1 is 3/2.
Yes.
But 3/2 is in the denominator. So it becomes 2/3. So this becomes 2/3 x to the power of 3/2 plus a constant c. That is your function. A function that is derivative is that. That is good. You can stop here. So let me change my color. This is optional. But I want you to be able to simplify things a little bit. So you can stop here. That's completely okay. But you can write it as 2/3 and then write it in the thirds form. You can write it as x to the power of 3. Yes? Is that right? Because the second so the one that I am writing with green, you don't need to do it if you don't like it, but sooner or later you have to learn these things as well. So then I would do this like this. I would write it this, and then I would write x squared times x. Yes?
Is the camera fine?
Yes. Yes. And then what happens? X squared, and this one goes out, so it becomes 2/3 x square root of x. And I don't need to put absolute value, because x should be positive, otherwise my function doesn't make sense. So I myself prefer, of course I forgot to write c all the time, so you have to write c all the time. So I myself prefer to write it like this. This is more tangible for us than this one. Anyway, but this one that I have written in green is completely optional. Yes.
Why did 1x go out on the last part? Why
Because
did
x to the power of 2, and this is the square root of x.
Oh, okay.
This will go out, but this doesn't have enough power to go out, so this will be back. So x square root of x plus c. But I hope that you agree, it was not that easy to guess that this combination is the right combination for this. So this means that we are actually doing something, not just guessing. Yes? Okay, let me just increase the level a little bit. So number 4. So what happens, you probably know the rule now. F of x, let me just write it as 3x to the power of 2, the third root of x to the power of 2. Then I bet that you cannot guess, I think now. Can you guess a function whose derivative is this product? It's not that easy. So this means that we have to do it a little bit systematically to be able to answer that. But I think you know what to do, what I'm supposed to do, because you have enough experience by differentiation. This is more or less the same thing, but in a reversed order. By the way, if I give you this to differentiate, you have already had the exam. So how do you differentiate it? Forget about today's lesson. Just differentiate it. Yes?
Well, I would start with rewriting the third root of...
Because that's the only way.
Yeah.
Otherwise, we need another rule, which is called the product rule, that you haven't studied that yet. So the same problem happens here. If I want to do the primitive function, I have to do the same thing. Because the only formula relevant to this in this table is this one. And it only works if I have a power of x. Be careful, you are not allowed to solve this part and multiply it by this part. This is not true. I wrote and crossed it over, do you remember?
Yes.
Okay, so now here, what I am writing in blue is the solution, but not just capital F. I cannot start with capital F right away. So I would write 3x squared, and then I would write it as x to the power of 2/3. And now we can combine these two by the power rules, yes? So I would say that they have the same basis, so I add the exponents. This becomes 3x to the power of 2 plus, let us do it in our head. So 2 plus 2/3, what's the answer? 8/3, yes. I hope that you can convince yourself. If I add 2 to 2/3, it becomes 8/3. Okay, now everything is ready. Because I have a multiplicative constant, which it doesn't matter here, I know how to deal with that, and then I have a power of x, and I have the formula up there. So this means that I can immediately start the process of finding the primitive functions. So 3 is just 3, and then I would write 1 over, this number is playing the role of that a, so it becomes 8/3 plus 1. But the same thing happens 8/3 plus 1. And then because they have emphasized on all, I have to respect and put C there. Okay, can you just do this in your head again?
11/3.
11/3, so it becomes x 11/3, and then I have a constant. I'm copy and pasting these things. Okay, if this becomes 11/3, that is also 11/3. But it is in the denominator.
3
So
over
it
11.
becomes 3/11, and then as a multiplied by 3, 9/11. This is 9/11, yes. Okay. So you see, this is actually a nice. You couldn't probably guess this function will generate this after differentiation. If you don't believe, you have to check. But if you want to continue, let me just change the color, write it with green. This I agree, so by the way, I wrote it a little bit bad. So 9/11 should be close to this, yes. Okay, and then if you want to continue, you can, of course, to make it more understandable for us. I don't know, I prefer to write things in third signs, in third form, rather than fraction powers, but of course, that's up to you. If you want to continue, which is optional, so you just write 9/11, and then instead of that one, you write the third root of x to the power of 11 plus constant. But because this power goes beyond this number, I can pull some of them out. So how many of them I can pull out? So I can write the third, instead of x to the 11th, I can write x to the power of 3 to the power of 3, and then multiply it by x to the power of 2. Yes? 3 times 3 is 9, plus 2 is 11. But what is the good point? Because now this power here and that are the same, so I can pull this out. So this becomes plus c, of course. Then it becomes 9/11, and then this becomes x to the power of 3, the third root of x squared. But as I told you, this part is optional.
Baba,
Yes?
how much harder would it be if we did the product rule that we haven't gone through?
No, the product rule, we don't have any product rule for primitive functions.
We don't. There doesn't exist.
That you have to wait a little bit until
Yes.
university.
University.
Yeah. But the product rule of derivative, it's not much harder, but they have decided to put it in math form. Yeah.
But I can't. If I learn it, can I do it on the test, or you won't allow that?
Now you
It's
can do
easy.
that, yes. Okay. But be careful, that will not make it easier for you.
Mhm.
Because the product rules and quotient rules, whenever I myself can avoid, I will avoid them. Because the formulas are not that simple. Anyway, So you see this function is a nice function. So if you differentiate this function, it becomes that, and I hope that it is not possible to just randomly guess that function. So we are really doing something. Okay, and then let me just give you another example. So what happens if I give you this? Number 5. F of x, this is simple. So x to the power of 2, 2x minus 3 to the power of 2. Let me make it 5. You want to find all primitive functions for this function. So what I'm supposed to do?
Expand.
You have to expand. It's exactly the same. If I ask you to differentiate it, you have to expand. Here you also need to expand. Okay, so the first one, you expand. So it becomes f of x equals to, I just copy and paste x5 for the time being. I expand this one, it becomes 4x squared. 2 times the first one times the second one, and the second one is squared. The expansion is not fully done yet, so I just multiply it again. So it becomes 4x to the power of 7 minus 12x to the power of 6 plus 9x to the power of 5. And everything is now ready, yes? And you do it in your head mostly. So I have to use the first row 3 times. Once here, once there, and once there. So what can I do? Just do it in your head. What is x7?
8.
x8 divided by 8. Yes? 1 over 8, x to the power of 8. Yes or no?
Can you explain
A
that one more time?
7. A is 7. Gustav. A is 7.
Yeah?
You put
Yes.
7 there. It
And the
becomes
exponent
1
is 8.
over 7 plus 1.
Yeah?
7 plus 1. Yeah. 7 plus 1 is 8.
Yes.
So why do you
Yes.
say yeah? Yes, finished. Yes.
1
Okay.
over
Yeah.
2 x.
So then 1
power of
over
8.
8 that you have here and 4, it becomes what?
1 over 2
1 over 2 x to the power of
over
8.
8, yes.
Okay, just tell me what happens for the next one.
It's 12 over 7
12 over 7 with
x
negative
to the
sign.
power of 7. Yes,
X to the
negative.
power of 7. The other one,
Next one is
9 over 6. But 9 over 6 can be written better.
3 over 2
3 over 2. So there's 3 over 2,
x to the power 6.
6, and then a constant. Yeah, try to do a lot of things in your head. Otherwise, it is really hand-tidying. How do you say it in English?
How do you say it in Persian?
What?
That's what we're scared of. This is the Persian way of
Yeah,
doing
I
it.
understand that.
It will tie your hands actually. Yeah? How do you say it in Persian? I don't remember actually. خلاصه یه سری دردسر واسه ایجاد می‌کنه.
What is this?
Okay. So this is something, and let me increase the not the level, the type. So you see, the expansion is something that you have to have your head, the square roots, how to act with the search signs. So this is the same. And then, do you remember there was another type of problems I discussed when I was talking about differentiation? Do you remember what type of functions was that? Because in principle you don't know how to differentiate fractions yet, but you already learned some of the fractions, how to do some of the fractions. For example, if I give you this, can you differentiate this? Still you don't know the fraction rule, but this is possible that you do it in Math 3C. Do you remember how? If I ask you to differentiate this, how do you do that? Yes?
We write it as x over x
X over x
plus 1 over x.
plus 1 over x, but x over x is 1, but you bring this up, it becomes x negative. And then it is easy to differentiate. So these kinds of fractions, you can also find primitive functions. These kinds of fractions whose denominator is actually 1 term. Yes? But if I increase it to 2, then you don't know how to do it in Math 3C. Okay? So let me just give you some examples of that type as well. Okay, so number 6. Let me, for example, write it as f of x is equal to 2x to the power of 3 plus square root of x divided by 5x to the power of 2, and then let me put a minus 1 here as well. So this is not possible to guess, yes? If I ask you, can you give me a function whose derivative is this, based on just guess, it is not possible. Okay. Now, again, I cannot immediately start the process of primitive functions because I can only use these formulas and the roots, yes? So what can I do? I have to simplify this function and put it in a form that I can manage it. How? I would write f of x is equal to 2 to the power of 2x to the 3 plus this one, I can write this, minus that, and then divided by 5x squared. And then I need to divide them one by one, so this becomes 2x to the power of 3 divided by 5x squared, and the other one is x to the power of 1/2 divided by 5x squared, and then I have minus 1 divided by 5x squared. But then this is simple, because this becomes 2/5 of x. 2/5, and x to the power of 3 divided by x to the power of 2 is just x. This is 1/5, but don't, so you need to write everything in the numerator. So this becomes 1/2 minus 2. Because I am dividing, I have to subtract the exponents. But 1/2 minus 2, hopefully you can immediately realize it is minus 3/2. So then it becomes x to the power of minus 3/2. But what can I do with this one? This is useless in this form, because the only thing that I know, it should be a power of x. This is not exactly a power of x, unless I write what? Minus 1/5.
X to the power of -2.
Yeah, x to the power of -2. And now everything is ready. Because I can use the last formula, the second row, 3 times. Here a is 1, here a is minus 3/2, and here a is minus 2. And then of course you have to be a little bit careful. So here, now I start finally my capital F. So then it becomes, so can you do it in your head now? What is x? A is 1, so it becomes 1 over 1 plus 1, which is 1 over 2, but that 2 will cancel that 2. Yes? It becomes 1 over 5. X to which power? 2. Yes? Okay, it might be the other one is harder for you. But anyway, so you should be able to do these things in your head. But let me just write it. 1 over 5. And then what should I write? I should write 1 over. This is playing the role of A. So I have to write A, but I have to add 1 unit to it. And then I have x to the power of, again, the same story. I have to add 1 unit. So you see, in differentiation, you subtract 1 unit, but in primitive function, I told you it's the reverse order. You add 1 unit. Okay, and then what happens here? I have minus 1 over 5. A is this number here. So this becomes 1 minus 2 plus 1, and then x to the power of minus 2 plus 1, and then plus a constant.
Yes.
And then we have to simplify this as much as we possible. So f of x is equal to 1/5 x to the 2. Okay, can you calculate this in your head?
The first part is 2. 2 plus 1 and 1/5.
No, this one
Yes,
is
that's-
negative 1/2.
Yes.
And it becomes
it's
negative 2, so it becomes negative 2 over 5, yes. Negative 2 over 5, x to the which power? Negative 1/2. But what about this one? Minus 2 plus 1 is negative 1, negative 1 multiplied here is positive 1 over 5. And then you have x to the power of negative 1, and then you have a constant. For me, that's completely okay if you stop here, but I don't want to have negative
Yeah,
powers. That's
you're
just
right.
personal thing. So that is 1 over 5x squared. This, I will take it down, it becomes positive, and I write it as a third sign. So it becomes 2 5 square root of x, and then I will bring it down. So it becomes 1 over 5x plus a constant. Optional.
Yes.
It's more beautiful, yes. I think in the first part of the book they have started talking about all scenarios. And I think that's not a good idea. Let me see if I can stop here and give you some exercises to practice on your own, or I have to continue.
Is this a C-level question?
Yes,
This is A plus level.
No. No, in this case.
I don't know. These are not hard. If you are experienced, for the first time, I would consider A-level question.
Uh-huh.
This is the first time you are being exposed to this concept.
Yes.
But if you go, this is nothing actually.
Well, of course.
Yes, because you will learn a lot of tricks to find primitive functions of different categories of functions later.
What do you mean? Can you see a different character? Like, can you? Do you have a trick for this equation?
No?
No. Sure.
Yes, but they have already talked about everything. I think that is too much if I want to process that one as well. Okay, I will stop here. Okay, and there are one group of exercises that you can immediately start working on them if you want to. So we stop here, okay? So this part is not included in the coming exam. You remember, one more session I will teach, 2 more sessions I will give you to practice for the exam,
Okay.
okay? Thank you very much.